to tell us about hydrodynamics in anisotropic.
Thank you very much. Good morning. Anisotropies make a difference. Now you can leave. So this is all I want you to take away from this. Anisotropies will make a difference in particular in hydrodynamics, and it was only after I studied for 5 years these different systems until I realized they have something in common, namely that they are anisotropic. And so today I will highlight the effects of anisotropy in the low energy limit of these holographic models that we've been studying, and there will be also hydrodynamic constructions that I will review that we've performed in some of these examples. So what are these examples? Anisotropies given rise by a magnetic field, so creating a difference between that direction along the magnetic field and transverse to it. Rotation, creating anisotropy along the rotation axis and transverse to it. And then you see a model, hydrodynamic simulation of a heavy ion collision here. And what this is supposed to illustrate is the Bjorken expanding plasma, where you have a longitudinal expansion and like no expansion in the transverse plane. So that's the types of system that I'll talk about. And I found it noteworthy that I'm very grateful to be back at the GGI again. So thank you to the organizers. Thank you very much. I was here last in 2018 when we actually talked about vorticity, which will be one source of anisotropy that I consider, and magnetic fields, which will be another source of anisotropy, which I'll discuss. That's me there. And I was here the first time for a workshop on ADS-CMT in 2010. So what I would like to highlight here is that we already talked about fluid gravity correspondence, and so this will have an impact on the hydrodynamic descriptions that I will be discussing, and the differences that anisotropies make in hydrodynamics. So why is it that I claim that anisotropy makes a difference? Well, hydrodynamics is an effective field theory based on symmetries. If you construct your constitutive equations or your generating functional, we heard yesterday about Schwinger-Keldysh formulation. I'm sure it's been discussed previously in this program as well. So then you can also talk about generating the Schwinger-Keldysh action or a generating functional. You would construct them out of all pseudoscalars, pseudovectors, and pseudotensors, which transform accordingly under the Lorentz group. And part of the Lorentz group, one transformation is also rotation. That's why I'm mentioning it here. So we'll talk about it in a second. Here's an example for the charge current, let's say, the vector current. This is a charge density, fluid velocity, and then you have at the first order and derivative in the gradient expansion, you might have a covariant derivative acting on a charge density n. And then you have higher order corrections in the derivative expansion, and that's the types of tensor structures that I'm talking about here. So this would be a Lorentz vector, this gradient mu n. Isotropy of space leads to a rotation symmetry, but if I break that isotropy by some anisotropy, for example, some sort of external vector field, or maybe by the state itself being anisotropic, like the cigar shape that we imagine when we talk about the first Fermi in the heavy ion collisions, then we have a breaking of that rotation invariance, and therefore we will be able to write down new Lorentz vectors, which would, for example, point along this vector field. So you could define a normal vector in the direction of this vector field that points in the direction of the anisotropy. For example, if this is a magnetic field, you could define this unit vector as b mu divided by b, the 4 vector of the magnetic field divided by its magnitude. And that is a new piece of Lego that you can put into your constitutive equations or generating functionals. So that will lead to more terms in constitutive equations, and that will lead in consequence to new transport effects. And I'm not the first one to consider this. In 2010, that was the first mention that I'm aware of what's called anisotropic hydrodynamics, first by Martinez, Strickland, and Florkowski and Wroblewski in these papers in 2010. The idea here is very much like what I was describing. There's a direction of an anisotropy that singles out this direction. And so here, that's a later review paper from 2018 where they say over time, this is the proper time, how different is the anisotropic hydro, so the solid line here, when it's from the viscous hydro. In this case, they used DNMR like as a framework, and so they compare these two calculations in terms of the what's the observable is the anisotropy, pressure in longitudinal divided by pressure in transverse direction. And so if you go to 4 pi times eta over s is equal 1, so that's somewhere in the ballpark that we expect. You see there's some difference between the viscous hydro and the anisotropic hydro. But really, this seems like it's not extremely different. So the question is, does this even matter in heavy ion collisions, right? Should we even bother with this? Don't we have more important problems to solve? Well, I can give you an answer for N=4 super-Yang-Mills theory, and as my initial sentence indicates, it matters. So it matters to the extent that this our beloved eta over s can go down to 0. So, for example, you have here holographic calculations. So that's how we calculate these N=4 super-Yang-Mills results at strong coupling. We used holography. And I forgot the reference over here, but it will show up later on. So here we have the anisotropy due to a magnetic field. And here's the strength of the magnetic field. It's an external magnetic field as opposed to a dynamical one. That doesn't matter so much right now, but this is a normalized magnetic field. So it's the magnetic field divided by temperature squared. So if you have B tilde of order 1, that's where the magnetic field is of order the temperature squared. And so what happens here is when you make this magnetic field very strong compared to the temperature, that's when you go to the right on this graph here, then this quantity that's plotted here goes down to approximately 0. And what's that quantity? It's the parallel shear viscosity divided by entropy density. So this is the quantity, if you have isotropy, that stays at 1/4 pi for the whole range, right? So there is another viscosity, a shear viscosity, which is eta perpendicular divided by s, which actually satisfies this 1/4 pi value in this holographic model. So you need to distinguish, is the message here, between shear transport in the longitudinal direction and shear transport transverse to the magnetic field. Yeah. Oh, sorry. The mu tilde is increasing from one curve to the other here, as indicated by the colors, and it's the chemical potential associated with the gauge group that you have with this magnetic field, right? So there's a U1. Think of it as electromagnetic U1. And this same gauge group, there's a charge density that's associated or thermodynamically conjugate to a chemical potential. And that's what this mu divided by T is that we call mu tilde. Other questions? Do we only have 2? There's more. There are more, yeah. So you can distinguish between shearing in the plane that contains the magnetic field. That's what we call the longitudinal one. That's the one that's plotted here in these the data here that we got from our holographic model. So that's what we call the eta parallel. And that's parallel because we're shearing in the plane that contains the magnetic field. And then every shear that is not containing the magnetic field in its direction, that's called the transverse shear, and there's 2 of those at a perpendicular. And then there will be more shear viscosities, which I can tell you in this example. I have a list. I'll show you. Other questions? Yeah, so the magnetic field here is not a probe field. This is, so when we go to the holographic model, this is magnetic field back reacted on the geometry. So there's a coupled system of Maxwell-Einstein equations that we have to solve. This is what we solve in the bulk, and then on the boundary, this corresponds to N equals 4 super Yang Mills, where you gauge the R symmetry, like a subgroup of the U1 R symmetry. Mm-hmm. They are. I mean, they are not dynamical, but they certainly back react on the system. So the value of the magnetic field determines the value of the transport coefficients, which is one way to see that the magnetic field back reacts on the whole. Maybe I'm not quite understanding the question right. Oh, yes, that will be my conclusion slide, my outlook. So I think we should. Yeah. Yeah, those are good points. It's normalized to, yeah. I have to remember my conventions. I believe it's normalized to L squared. Yeah. Yeah. Right, so you can think of this as, so this is like a Lorentz gamma factor exactly. This is something you can think of this as the velocity divided by the speed of light or something like that. This one, I have not explained it yet. Happily, thank you for the question. So moving from the magnetic field to the rotation, there is 2 Kubo relations that you can extract. Well, okay, like I should be more careful here. So there are 2 equations that you can extract from our data that give you the relation between the shear viscosity at zero angular momentum, so when nothing's rotating, which is 1/4 pi for both of them when you divide it by s. And so that's without the angular momentum. But when you switch on angular momentum, then you have this enhancement, well, suppression by a Lorentz factor, I would say. The S also depends on this kind of Lorentz factor, the entropy density. So when you work out what eta over S is in those 2 cases, then you find that the transverse shear viscosity, that's the solid line, is 1/4 pi times the entropy density. So it satisfies the bound that Pavel and friends found for holographic theories, Einstein theories. And there's this suppression here in the longitudinal shear viscosity divided by entropy density. Because the Lorentz factor of the eta parallel conspires with the Lorentz factor showing up in S, such that you have this suppression here. Yes. Yeah. Mm-hmm. Exactly. Yeah. Yeah, I believe I have an equation that makes that a bit more clear right now. It's a bit more of an advertisement to compare that this effect of suppression of one of the 2 shear viscosities, namely the longitudinal one, happens in both the magnetic field systems and the rotating systems. That's the message. There's a qualitative difference really between the shear viscosity that's transferred, which is behaving like we expect. Eta over S is equal to 1 over 4 pi for this holographic systems. No matter how fast they're rotating, no matter how strong the magnetic field is, this is always 1 over 4 pi for this one shear viscosity. But for the parallel shear viscosity over entropy density, it can be suppressed down to 0 due to strong anisotropies. That's the message here. So there's a qualitative difference that is caused by anisotropy, and there's a large quantitative difference. Okay, that's the message. And so my outline this was the motivation to outline is that I will motivate and show how we calculated this in the strong external magnetic field and how we calculated this in for large vorticities, or rather I should say fast rotations is probably a better way to phrase this. And then also, if I have time, I mentioned that in the Bjorken expanding case, we're working on calculating the speed of sound, which is different along and transfers to the expansion direction. So just to understand what I've been doing, for this case of strong magnetic field, we have both. We have a holographic calculation, and we also have a construction of the effective field theory, which we call hydrodynamics or chiral hydrodynamics in an external magnetic field. So we do the usual thing. We consider this as an effective field theory, means we are writing down an expansion in small gradients for the constitutive equation. There's the energy momentum tensor, the vector current, and an axial current in general. Then we want to take into account large temperatures compared to the frequencies and momenta of excitations around some equilibrium state. And the conserved quantities will survive after a long time. There's a conservation equation with a Joule heating term here. Oops, sorry. Sorry. I should, oh, I see. Because now I defined what I'm talking about. Okay. On the right here, this. Oh, sorry. Yes, this is the Joule heating that you get when you have like a current that's generating friction. So it's the vector one in this case. Yeah. Yeah. It would be there if I didn't. Yeah, it's the vector one. Mm-hmm. That's right. Sorry about the missing label. Yeah. So then the idea is, what kind of limits are we looking at? I mentioned a large temperature compared to the excitations, frequency and momenta. But then we want magnetic fields which are not suppressed in the derivative expansion. So I call them order 1 in the derivative. And then B is much smaller than temperature squared. That would be the regime that is interesting for this description here. Note that the holographic results that I've shown you, I've plotted to very large magnetic fields, right? So that's not the regime I'm talking about in this description. This is only covering a very small range of the holographic results that I've shown you. Yeah. Mm-hmm. So if you, yeah, so in this is a conformal, so the holographic model is a conformal theory, right? So every scale that you introduce matters and gives you another measuring stick. And so all this does for the holographic theory is that it gives you yet another scale on which something can happen, like a phase transition could happen on that scale. Like if you don't have a scale to set, like that's the temperature at which a phase transition happens, then no such thing can occur. So this is how you should think about the B as just another scale in a conformal theory, and it is. Oh, It's a thermodynamic quantity. It's a thermodynamic label which labels your state, just like an energy density does, or temperature. T is also order 1, yeah. Oh, I see. So what that means is that yeah, good point. So we are not suppressing something that's order. Well, in a sense, you could think of it as neglecting higher powers of B. Yeah, I see what you're saying. So okay, so what it means is practically, I cannot describe with this effective field theory that I'm about to introduce, I cannot describe anything to the right of order 1, B tilde order 1. So if I try to use my effective field theory past that, like to the right, then it will fail. That's what it means practically. Hmm. Well, it's not, right? So B is order 1, it's not derivative order. Just like the temperature is not derivative order, it's order 1. It labels thermodynamic states. As such, it's not suppressed in any way. And let's forget about this for now, okay? So I have to think about it too. There was an argument why we wanted this, and I have to think about it more carefully. Okay, so this is the description that we're constructing. Well, we're using standard methods. One is to use the entropy current, and so here's an example. We construct the constitutive equations in this example here for the current. It could be the vector or the axial current. Both have a charge density which flows with the fluid flow. And there will be corrections here, gradient corrections. One of them is, for example, also the vorticity vector, which is defined in this way. And then basically you puzzle together these tensor structures, all the possible ones that you can form out of your hydrodynamic variables and their derivatives and the metric and the epsilons, the antisymmetric tensors. So that's how you generate the constitutive equations. Alternatively, for everything that does not produce entropy, you can also construct, and we did construct the generating functional, and then from the generating functional, you can also derive 1-point and 2-point functions if you are not producing entropy. So by now there's methods that do the whole derivation from Schwinger-Keldysh and so on. This is not what we do here. We have a hybrid approach where we for the dissipative stuff, we're using the entropy current argument, and for the stuff that is hydrostatics, or like that's sustainabilities eventually, those terms we derive using a generating functional that we construct in this way. Okay. So then we restrict this by conservation equations. Here's an example: continuity equation relates the charge density derivative to the gradient, to the divergence of the fluid flow, and then we use the positivity of the local entropy production according to this formula, and that gives us, with these symmetries, the most general hydrodynamic 1-point functions for chiral charged fluids in a strong magnetic field, external magnetic field. That's what we generated in this paper here, constructed in that paper. And then with these 1-point functions, you can take variations of them with respect to the sources and thereby create 2-point functions. And those 2-point functions will then give you Kubo relations. So I did not want to go through this in detail because I'm sure everybody has seen a Kubo relation. A Kubo relation relates a transport coefficient to a two-point function. And what I just said is the method to derive it. So just in a simple example, that's 2 plus 1 dimensional. You have a current here that has some sort of constitutive equation. This is just an example. I've set a few things to be fixed just to make things simple. I set the temperature and the fluid velocity fixed. And the only thing that changes is the charge density here. And then you can write down the one-point functions from the constitutive relation. And then you use the conservation equation in expressing, oops. And I start again. Sorry, I use the equation of the conservation equation here for the current in this example to derive this form here of the denominator. And with a few redefinitions, we get exactly what we expect for the Kubo relation for the conductivity here. That is, it's related to the charge current in the x direction. The two-point function of it with itself at zero momentum, but at a frequency which you first divide by that frequency, and then you send that to zero. And that gives you the charge conductivity. Okay, so this is just a quick review of where Kubo relations come from. That's what we do. But then there's a surprise. So first of all, when we have a magnetic field where the current is, this J is along the magnetic field, let's say that's along the Z direction. So we're calculating the parallel conductivity parallel to the magnetic field. We get exactly that type of formula that I just motivated. It's related to the two-point function of the current along the magnetic field. But now there's a surprise. So the perpendicular two-point function, which is now a current transfers to the magnetic field. If you look at that and just take the same formula on the left-hand side, you get a term on the right-hand side, which is not the conductivity, but it's the resistivity. And it's suppressed by 2 orders of the frequency. So this is just something that you find when you write down these constitutive relations and vary them according to what the principle that I just said. Yeah. Yeah. So this good observation. So that if you write this down in carefully, not setting k to 0 and adding a few more terms, then you could create that. But here, this is already in assuming that B is non-zero. So it's correct that in this particular way that we write this, you cannot see how there's a smooth B equals 0 limit. It's similar to as if you scale some quantity, some observable with the temperature, and then you want to take a 0 temperature limit, then yeah, this is also bound to fail, right? That's correct. Yeah, if you ask me for the details, I have to look back into exactly how this expression looks before you set k to 0. But I remember there's a bunch of 1 over b's, and like then there's this. So basically, I mean, one thing I believe that happens. I'm not sure if that gives rise to exactly this behavior, but this non-limiting behavior. But there are terms that are something like k squared over b, and that right. So that would ruin the smooth limit. Okay, sorry, this is probably a bit unfortunate. So on the right-hand side, I should also have this. There should be a big bracket around the whole equation. So the limit is taken on both sides. This is just to indicate that this resistivity term shows up at order omega to the 3 compared to an order omega where this shows up. That's all this is meant to show. It's in this enthalpy for one. This is essentially epsilon plus p. That's what this is. Sorry, what? W0 is epsilon plus p. It's the enthalpy. And then this coefficient also depends on the temperature. Yeah. And the resistivity depends on the temperature. So I don't have a plot for the resistivity, I think, but I have some other transport coefficients. Good point. So in this case, I'm only considering one U1. So if you think back to the Sonsurovka paper, we're doing the same thing. So we're using a holographic model which has only one U1, and that's the U1. So in sense, you could call this the vector current for intents and purposes of this equation and these Kubo relations. Okay, so upshot here is that you get very different behavior and very different Kubo relations in the transverse versus the longitudinal direction to the anisotropy in relation to the anisotropy. So not only the Kubo relations are very different, but also the values of the transport coefficients. So I'll show you those once we move to the holographic model. But for now, I just want to point out. Yeah, of course. Say that again. We do. It's in fact we have a shear Hall viscosity, shear-induced Hall viscosity and Hall conductivity. I'll show you. Yes, good point. And so let me show those some of those. So first, the more boring thing because you guys already know, I told you, there's a shear viscosity in the perpendicular direction, perpendicular to the magnetic field. So you might have a shear like this shear flow in the XY plane, and the magnetic field pointing in towards us in the Z direction. And then you have this standard formula of Txy, Txy. And you take its imaginary part, divide by omega, take the limit omega going to 0. That's what the shear viscosity in that transverse direction is. This is the usual formula. But for the parallel one, there are some extra contributions in this. Oops, sorry. Sorry. There are some extra contributions in the lower formula for the shear viscosity in the parallel direction. So parallel to the magnetic field, I have this shear in the XZ plane. And so there's a term on the right-hand side that is proportional to the perpendicular resistivity and to the Hall resistivity. So there's the Hall resistivity playing a role in this Kubo relation here. And this is a TXZ correlator, just like you had a TXY for the XY plane shear. So you don't do anything crazy here. You just calculate the 2-point function that you would calculate for your standard shear viscosity, and you find there are some extra contributions. That's number one. So the value of the shear viscosity depends on the direction of the magnetic field. The Kubo relation depends on the direction of the magnetic field, and this can lead to the creation of flow at early times. That's a claim that I have to motivate. So as far as I understand the Bayesian analysis, all the analysis that people are performing to analyze the data is assuming isotropic shear viscosities. And so what I'm saying is we should take a look at what anisotropic shear viscosities, so different values along the anisotropies and transverse to the anisotropies, do to these Bayesian analyses that translate position space anisotropy into momentum space anisotropy. So that's basically the message. And for this particular slide, so there's a few transport coefficients more. So before I come to the Hall stuff, I chose a particular new Hall transport effect. So this is a Hall transport effect because it's an what people call an odd transport effect. So it's parity odd. That's what it means. There's an epsilon in the tensor structure in the constitutive equations. That's another way to say it. There's an epsilon in there. And so this is what we call C10, the shear-induced Hall conductivity. Well, what is that? If you have a shear in the YZ plane and the magnetic field still points in the Z direction, you will measure a charge current in the X direction, so perpendicular to this. So this tells you, this comes from the epsilon structure in the tensor structure. You have a charge current response in a direction that's transverse to the plane where you perform the shear. So that's the kind of the Hall part of this. It's an unexpected direction. And it's parity odd, and it is non-dissipative. So it's a novel Hall response that does not produce any entropy. And it's an interesting interplay between the charge and the shear sector of the theory. So you just note that you just shear the fluid flow. You're not manipulating any charges, but then what results from this shear is a charge current. So that's a novel type of response. And the Kubo relation that you derive for it is TTX TYZ. So these are the components of the energy momentum tensor that you have to look at. So we should look for that transport effect. And another thing that happens is a certain susceptibility, M2 it's called. It's a perpendicular magnetic vorticity susceptibility. Well, we call it that because it's a response to vorticity and equilibrium. And it's not just the fluid flow velocity, it's the magnetic vorticity, so which is defined as the antisymmetric product of the sum of the magnetic field. So if you think of this term, this omega b, it's structured just like you would define a fluid vorticity. But so with an energy, with an epsilon tensor that's contracted with a fluid velocity and the gradient of the magnetic field, not of the fluid velocity in this place. So that's why we call it magnetic vorticity. And this is in susceptibility. So this is an equilibrium response, meaning the frequency is zero, so no time dependence needed. The Kubo formula first sets the frequency to zero and then the momentum to zero. And you calculate this TXZ, TYZ correlator. And the point is you can do this since it's equilibrium. It doesn't really involve time dependence. It can be computed on a lattice. And I asked my lattice colleagues and they say they can do it. So I'm hoping they are working on it right now. Then there's the test. Can we test these Kubo relations already now? So that would be my question. And that's where we have to move to a holographic model. So the answer is yes, we tested these Kubo relations in a holographic model. Yeah. So maybe I forgot to give you this. So let me say one thing that I forgot to say to this slide. So I wanted to give you this physical picture. Actually, why are the conductivities along the magnetic field so different from the transverse conductivities? Let me answer that. So let me take that occasion to. So why are these so different? Well, if you have a charge carrier that's moving along the magnetic field, it doesn't feel a Lorentz force. It just goes. It's transported as usual. But once you have a magnetic field and you move transverse to it, you have a Lorentz force that leads your charge carriers onto a cyclotron orbit around the magnetic field lines. So basically your magnetic field pins the charge carriers in the transverse direction and doesn't allow them to transport anywhere. They're sitting there. You could think of this as, some people say you can think of it as Landau levels. There's more physics to Landau levels, but which I'm not sure is in agreement with this strongly coupled system here. But yeah, this is the way that you can imagine that the charge transport transverse is inhibited while it is freely, charge carriers move freely along the magnetic field. Now, the question that you asked was different. Mm-hmm. Mm-hmm. Yeah. Okay, so I'll jump to this slide. These are all the coefficients that you want to see. So I believe what you're describing, that effect does not have a separate coefficient that's related to the chiral magnetic conductivity. Is that right? Mm. Okay. Okay, good. I believe it's a higher order term in B and derivatives that we didn't write down in these relations. Okay, so this is, now I can give an answer to why did we want to have small b, or b of a certain order suppressed compared to the temperature. That's because if we otherwise derive these Kubo relations like these here, there's a whole bunch of terms that would contribute. So we need some way to organize them, and then at this point we want B to be smaller than the temperature, so that we can, at least for the sake of deriving Kubo relations, those Kubo relations are now valid for like small b compared to the temperature. So that's an answer to an earlier question that you had. And now, as an answer to your question, I believe it has a similar answer. This negative magnetoresistance would show up as a higher order term in B, like a correction to Ohm's law. Yeah, yeah, and we don't, like in the holographic calculation, it's included. Yeah. Well, for the sake of the derivation of these Kubo relations, we need something in a low. We're calculating these transport coefficients in a low temperature. Sorry, in a high temperature approximation, but for a magnetic field which is much smaller than the temperature scale. So otherwise, we have no hope to get these relations. So we could look for that. I mean, we have the Nernst effect, for example, we saw, and how it's related to these transport coefficients. So, but okay, so those are all good questions, and let me just say that we've tested these Kubo relations now in a holographic model. So that's our microscopic model, our version of kinetic theory, or whatever you might want to call it. You know, QCD, perturbative QCD, is of course an approach to test your Kubo relations to use them. We calculate these values of the transport coefficients in a holographic model, which is dual to n equal 4 super Yang-Mills theory. So we construct the dual, which is dual to a charged plasma state in a strong external magnetic field. So this is basically an Einstein-Maxwell action. So you have this Einstein-Hilbert piece with the negative cosmological constant here. You have the Maxwell term F squared here, which encodes the dynamical electromagnetic fields in the bulk, which are dual to a global external field in the boundary. And we have a term that is a 5-dimensional Chern-Simons term that encodes the chiral anomaly in the dual field theory. So both of, like, the chiral anomaly breaks parity, and this one breaks parity as well. You could think of it this way. And then we find solutions which are generalizations of the Doka-Krauss charged magnetic black brains. So they carry a charge. In addition to, like, the Reisner-Nordstrom black hole, a charged black hole might be familiar to you. In addition, we also give it a magnetic charge, in a sense. and that is asymptotically ADS5, this metric that we get from this, that solves this. And so we get charged magnetic black hole metrics, or black brane metrics, really. Okay, and that's the setting, and then we perturb around those states. So we perturb the background, the charged magnetic plasma. We perturb that, and then we look at what the 2-point functions are, the responses, and use the Kubo relations to calculate the values of the transport coefficients. And what we get is, I just show you examples here. So this is this M2, this susceptibility that we talked about, a response to the magnetic vorticity in equilibrium. The different curves are the different strengths, increasing in magnetic field from red to purple. And you don't see a huge difference there. Here, this is what we called mu tilde earlier. It's mu divided by T, the charge chemical potential, normalized to T. And then you see that there is the shear induced Hall conductivity, C10, that I advertised. That's this new parity odd coefficient that produces no entropy. And this C10 is 0 if you have 0 chemical potential, but as you have non-zero chemical potential, it increases with the magnetic field. So we find that the Onsager relations are satisfied between these transport coefficients. We find that all the Kubo formula are consistent with each other, and everything's finite. So we were happy to see that everything fits together in this holographic model, and you have non-zero values for these transport coefficients. Okay, so I pointed out there's a lot more. So we have a whole sector that is Hall physics here. So the transverse Hall viscosity and the shear-induced Hall conductivity. It's in regard to the earlier questions. And there's the Hall conductivity in the perpendicular direction. The Hall conductivity in the transverse, in the longitudinal direction happens to be 0 in this model. We have no good reason why that is so, but yeah. The transverse one is non-zero. The transverse Hall conductivity is non-zero. And we have Kubo relations for that one. But the point is now, is this relevant for the quark-gluon plasma or condensed matter systems? And in part, we explored this with Björn Schenke and my former student, now postdoc, Casey Cartwright in Utrecht. We looked at this chiromagnetic conductivity out of equilibrium. So this is the paper if you want to look a little more into phenomenology. But really the bigger question behind this is, which one of these many transport coefficients is relevant for phenomenology? And I just pointed out, like shear viscosities can be qualitatively different, and so can many of these other transport coefficients, which are relevant for the quark-gluon plasma. I do not know. I'd be happy if anybody has intuition on this. But also just to mention, there's there are some other viscosities that show up here, and Shugang, you asked about these other shear viscosities. I believe they're in this sector here. You find them in this side of the table. Okay, so we can talk more about this and look more at this. It's not what I want to waste your time with. I have about maybe a few minutes, 2, 3. Yeah, I don't want to torture you with even more of the same. But let's just move on to this other example that I have. And I was thinking that I probably run out of time. So let me be brief on this and just say, well, in this system where we consider a rotation, like a rotating background, we also we can model that background holographically, and we can then calculate eigenmodes. So in particular, sound modes and momentum diffusion modes indicated here, and with the paths through the complex frequency plane. And here are the dispersion relations. And the important thing here is that we can extract these dispersion relations from quasi-normal mode frequencies. Well, how does that work? Well, probably everyone is familiar with this linear response notion here, that if you have a linear operator acting on your excitations and that's 0, you can write the Green's function here and get the delta function on the right hand side, and then this gives you a way to invert this equation so that you can express the, for example, diffusion Green's function as the inverse of this operator formally, and that gives you this diffusion fraction here, or the denominator, the diffusion pole in the denominator of these Green's functions. So from this you can calculate these particular dispersion relations from quasi-normal modes in holography. So basically there's some equation, of fluctuations that encodes exactly the same information, and involves in particular for our calculations here for this rotating case, the fluctuations of the metric. And so we use this notion. Here's an example of two types of fluctuations. We have in the momentum diffusion mode, it's dual to the vector fluctuations, which are fluctuations of the metric in time space direction and the metric in time, and then the direction in which the momentum flows, which I believe we chose to be z here. And then you have sound modes, and these sound modes you would find in the scalar sector of the metric. The scalar sector having 2 time directions in the metric, or time and then the momentum direction z, or 2 momentum directions. So point is, you can classify this and separate these into different sectors and solve the fluctuation equations and find the quasi-normal mode solutions. And then the idea is compute the quasi-normal mode frequencies as a function of the momentum. These are fluctuations around rotating black holes, and then we have dispersion relations for these sound and momentum diffusion modes as a function of how fast is my background spinning. And that was parameterized in the first slide that I showed by A, which is kind of how fast is this spinning. And so this is the metric. You can ask me more details about this. This is a picture of earlier time, later time of the state in the rapidity direction versus one of the transverse directions, x1. And here's an intensity of the plot of the energy density. Theta is some form of energy density, some normal, some unit, energy unit. And so you see that density plot is the distribution is separating into 2 blobs over time. Separating along the x1 direction. This is not so important, but the point is this is an analytic fluid flow that we can extract from this rotating black hole on the boundary. It's analytically known, and it encodes like rotation and vorticity. So you can calculate, for example, the vorticity vector, and it's non-zero on this flow, and this is a solution to the Navier-Stokes equations. Yeah. Okay, because of the picture that you showed. If you look at it, it depends on the projection. So what we do is, in order to go from here to there, we needed to perform a stereographic projection because these ADS5 black holes, they are defined on a spatial manifold that is not X, Y, and Z, but 3 angles. So it's defined on an S3. And so now we have to stereographically project this onto a 3-dimensional, something like a Minkowski space. And so depending on that stereographic projection, like how exactly we choose the coordinates, I believe you could you could probably make this look homogeneous. Yeah. Yeah. Oh, I see. Yeah. So this is actually the major contribution that was done in this paper that I'm about to show now. So yes, so you need to find a mode decomposition that is like Fourier modes, but which are solutions on the S3. And they exist, so they are Wigner functions. They are a little bit like generalized spherical harmonics. And so yes, you need to use those eigenfunctions on the S3 to decompose your fluctuations around this background. Yeah. The omega and the k? Yeah. So good question. Do I have this? I don't have it explicitly in the main talk, but let me describe it maybe along this dispersion relations. So you see this is the nu, which is like a frequency, and there's a j here, which is like a momentum. And j is basically, you can think of this as like one of the angular momentum labels of these eigenfunctions on the S3. Similar to spherical harmonics have labels, right? And some of these labels are the eigenvalues of L squared, and the other label is the eigenvalue of the LZ, the angular momentum operators. And this is just a generalized angular momentum algebra, basically with 3 labels. And this J is one of them. And if you look at if you stare at this long enough, it looks like if you were to take the limit of non-rotating solutions, this is the label that coincides with the K that we are used to, the momentum, the linear momentum that we're used to. Okay, I promise not to draw this out too long. I'm happy to show you the detailed results. The point here that I wanted to make is similar to the shear viscosities, which I showed initially. So that's the equation that you asked earlier about. Here, these shear viscosities. There are similar relations involving such Lorentz factors involving how fast is my fluid rotating, involved in the diffusion coefficient parallel to the rotation axis. There is a speed of diffusion now, because you can imagine if your background is moving but you're not moving, then now like it looks like your modes that previously were just diffusing have now a velocity, and so that's what's in here. The speeds of sound are changing, as you see here, by factors of a, and this comes all from these dispersion relations, which actually can be written down in a closed form. And Pavel will know these very well, because these are exactly the relations that he wrote down for this dispersion relations of a boosted fluid. Because in this particular large temperature limit that we look at, the high temperature limit, the dispersion relations of a rotating black hole, fluctuations around the rotating black hole, look like a boosted fluid. And this look like is very important, because it took us 5 years to understand that that's the case. So it's not as obvious as you think, and I'm happy to discuss it in detail. But the state itself is a rotating black hole. It's fully rotating. But once you go to the high temperature limit, the fluctuation equations perceive the background as if it was only a boosted fluid. So there's a bunch of terms that don't contribute, and I'm happy to discuss this in more detail, but take my word for it for now. Yeah. You would think so, yeah, but it's not that. So our solution actually includes more contributions, and we actually also expanded in this limit that you're describing. And there are more terms, but it turns out that they cancel in mysterious ways. So yeah, it's a bit more complicated. In principle, you would think if you have a large sphere, like a black hole with a large radius, meaning a large temperature, and you zoom in on a small patch that lives on the horizon, and moving in that direction at this instant while the whole sphere is turning, then locally this looks like a boosted fluid element. So no, it's not quite that. It's a bit more complicated. Maybe there's a way to look at it that way, but we haven't found it. So there's an intricate way in which this happens. So I mean, one way that you can see this is from the results here, because we wanted to check when is hydrodynamics valid, and that means we make this sphere smaller. So we bring the horizon closer, So go away from that limit that you just described. So make this a smaller black hole such that the volume element actually is starting to feel the effects of rotation and inertia and so on, rotational inertia and all of that stuff. So, and we see that in the results in the dispersion relation for example, momentum diffusion, we see that the beta and the alpha are changing from their values 2 down to smaller radii, smaller temperatures, they go down to 1. So changing the dispersion relation here. And well, okay, so for the beta, beta is unaffected. So this is more just a diffusion term here that is affected. But yeah, so we see that change happening from the standard hydrodynamic dispersion relations as we go to small black holes. And somewhere there's a window, that's what this, so the upshot is really this, there's a window of horizon values somewhere between horizon radii 1000 and 10 to the 7, where the hydrodynamic behavior is hydrodynamics and you have convergence in like, it's within the radius of convergence, and it's distinct from a boosted fluid. So it's more complicated and more interesting than a boosted fluid. So there's that regime in these, where these black holes give you a non-trivially rotating fluid and non-trivially rotating hydrodynamic states. That's we had really tough time to extract numerics from that. And then also at those values, I'm not sure what to make of momentum diffusion dispersion relations where this alpha here now has fractional values. So it goes from 2 down to 1.5 and 1. And I'm not quite sure, like this is between 10 and 1000. I'm not quite sure what to make of this really. Is this a breakdown of hydrodynamics? Probably. So I just don't want to talk about hydrodynamics at that point. But above 1000, the only thing that happens here is that the values of the transport coefficients changes. And that's why I'm saying there's a window, there's a regime of validity of hydrodynamics with the standard exponents that we know, but the values of the transport coefficients are non-trivial. They're not just a boosted fluid. Yeah. Yeah, they are. Like, that's a good question, but yeah, this happens to be in a stable regime. There's a regime if you go to smaller temperatures where you have instabilities. And there's instabilities of the S5 in particular that we can talk about. But so because we have to, like I only showed the 5-dimensional metric, but this is really a 10-dimensional space-time which this all is embedded in. And there's this metric, this ADS5 cross S5. And actually the destabilizing modes live on the S5. So the sphere gets all wobbly and leads to a phase transition into a phase that some of our colleagues have figured out what that phase is, but we're far away from that. I'm happy to talk about instabilities. This is all stable, yeah. 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 It's essentially the radius of the sphere squared that is roughly so the radius of the sphere, this S3 that I was saying that this black hole XYZ live on, the spatial part of this black hole metric lives on a S3. The radius of that sphere, it's associated with the ADS radius, and that's what we call L. And so that radius sets the scale on which which you don't exceed when you have angular momentum values or speeds. If you exceeded it, it would lead to a super radiant instability. So it's like if just but it's basically like faster than light. You're trying to yeah, that's the causality bound. Yes, exactly. Yeah, I believe we know all of them. So all the known instabilities we've checked, and so actually we've checked all the fluctuations, all the metric fluctuations around these rotating black holes, and all of them are stable in the regime of radii that we look at. So that was similar to the question that you asked earlier. So it's all stable. Yeah, that is a good question, and we were worried for a long time there, but it's all stable. I see. Yeah, yeah. Yeah, we should talk about that. Maybe there's a simple criterion here as well. But as promised, I didn't want to keep you for too long. I already kept you longer than I wanted. So, and I feel we're already in the discussion session. So let me just say that we now are, and that summarizing what I've talked about, we have considered 3 examples of anisotropic systems: a strong magnetic field, a system with a rotation, and a Bjorken expansion. I didn't really get to tell you details about that. Ask me later. There's novel transport coefficients and very different Kubo relations resulting from this. So drastic differences, for example, in the specific shear viscosity that drops to 0. And we saw that the anisotropic hydrodynamics would be needed if we can say that the quark-gluon plasma of QCD is somewhat like N=4 superbearing Mills suggests. And so then what I propose is to calculate these novel transport coefficients on the lattice, and there's some perturbative QCD calculations by Igor Shavkovi and colleagues already, and then there's an effect of anisotropies on the elliptic flow, which I asked about, right? So should we rethink these Bayesian analyses to include more than one shear viscosity and more than one bulk viscosity? And then the question is, can we construct, and I think we can, a holographic heavy ion collision to model the quark-gluon plasma physics? Well, it will not, of course, not be QCD heavy ion collisions, but we're actually very close to having this this type of model. All the ingredients are there, and the codes are there. We just need to put them together. And then the question is, can we use these holographic codes to test formulations of hydrodynamics? And with that question, I will end. Thank you for your attention. There is no lower bound. It's even worse. Like, that's what I mean by qualitative difference. There is no lower bound for this one because what Pavel and friends derived falls in the category of, like, these are tensor excitations. And in Einstein gravity, you can show that these types of excitations can basically, by symmetry arguments, always have to satisfy a certain lower bound. In Einstein gravity, unless you add like Gauss-Bonnet higher curvature terms, it will always be 1 over 4 pi is equal to eta over s. But these other like shear viscosities that I showed, the longitudinal ones, they don't fall into that category. They satisfy different dynamical equations of motion. They couple to other modes. They're in a different sector now because you broke symmetry. And there's still shear excitations. You still shear one fluid phase against another. So nothing has changed in that, but then the response is very different. Mm-hmm. Extreme limits, yeah. So, yeah, yeah. I believe in the holographic. So the example that I showed. Okay, maybe go back here. This is maybe the one that you there. That's the picture that you have in mind, right? So for the rotating case, you have the strict limit of eta over s going to 0, really only in this causality bound, this absolute where stuff moves with the speed of light. And in this case here, you never really reach this. I mean, this is numerical data, so you can make the magnetic field compared to the temperature as large as you want. So you will never really reach 0. So with that caveat, yeah, in principle there should be some limit. Yeah, in this case, yeah, and here with where the rotation is as strong as strongly rotating as causality allows you. Mhm. Yeah. Non. Um, no. The simple answer, and to an extent, we overstretch our welcome within the hydrodynamic Kubo formula here, right? So what this is, I told you basically, this is holographic data, and the holographic model, as you say correctly, like that doesn't care about any bounds limits on limitations of our effective description. So the holographic model knows this, but have I really plotted eta parallel over S when magnetic fields are of order 100? Or is my derivation of the Kubo formula that I used to holographically calculate eta parallel, is that still valid here, or is that not valid anymore? So for that, yeah, I mean, I can only say we were surprised once we took some of the corrections into account, how well these were still satisfied, these relations. We had a previous paper where the magnetic field was of order derivative. And so I can only extrapolate one from that stepping. So we went from magnetic fields that are weak in that order sense order derivative into the regime where the magnetic fields are of order 1. And many of these relations still held up. They held up very well up to large values of B, for example. And I know this is not quite the answer, that's why my initial answer was no, but it seems to me there's systematic ways to extend this framework. How exactly this would work, how would the time, so you mean in the holographic model? But the holographic model knows already about everything Uli asked about, right? So, I mean, we have an anisotropic state that has an external magnetic field, and the holographic model, whatever I calculate is correct. Can I still calculate Kubo relations? That might be less meaningful. I can calculate 2-point functions in holography, and they will be valid, but can I relate them to something that I call a transport coefficient? That yeah, yeah. Well, without saying anything about hydrodynamics, I agree. Like the holographic model, you can calculate correlation functions, time-dependent ones as well. Yeah, that's not a problem. And you say so? Is like these solutions, are they non-perturbative in the like anisotropy? Systematically, I'm not sure how to do this in our. I mean, yeah, yeah. Maybe imitate something like what you, Strickland, and Wroblewski and Florkowski have done. Yeah, yeah, I'd be happy to discuss. Yeah, definitely. Hmm. Probably. So first to relate, this is. Ah, okay. So you would need a vector and an axial current for that, right? Yeah. So one thing I did not say, we first did this analysis in 2020 paper only. Well, I mentioned it once. We did it only with one U1, so there's really only one current at the moment. We have calculations which are two currents, and which have a U1 axial and a U1 vector. And so as a general, what we see in those calculations that we are performing now, like all the effects that I talked about, have a twin, like a dark twin, an axial twin. So this will have a C10 axial likely. It will probably have different symmetry properties, but it will have similar tensor structures. So there will be some C10 tilde or whatever. Thank you.